Hey everybody, good morning or good afternoon. I wanted to spend some time. I've just posted a couple recordings on file systems. I've got one more to complete, and so we're going to kind of circle around and look at the underlying storage mechanism that sits beneath the file system. And traditionally it was a disk drive system, but today it could be flash memory, as we're seeing in a lot of Mac computers and phone computers and things. And so the nature of mass storage is going to change, so it's just going to be a more logical thing, and so we won't necessarily tie it to a disk drive so much in the future. And ideally, as we're seeing technology evolve, we're going to just see faster and faster systems, larger disk drives, kind of still in alignment with Moore's law. But even seeing technology changes, such as more integration of flash-type memory as our mass storage. And we're seeing that today in a lot of the computer systems that are even available on the market. So we're going to kind of drill down and take a look at mass storage and the underlying disk structure that the file system kind of hides from us. And so the file system and its implementation and the recording on the file system implementation, we'll walk through a little bit of this, actually sits above the disk drive and takes the idiosyncrasies of the disk drive out of the loop. Most disk drives will follow a standardized format, meaning where they store information, how they store information, and so it just becomes kind of technology differences in terms of their sector size or their rotation speed, their time between failure that differentiates one disk drive from another. And we'll talk about that some today. And so again, we're going to look at ways that we can improve performance. We know that the disk drive is a mechanical device, and so because it has moving parts, it's going to operate slower than our computer chips and our random access memory primarily. And so we do things at the operating system level and at the disk level to try to optimize all disk operations to minimize the mechanical nature. And so we'll take a look at some disk scheduling things that control which sectors get read, which sectors get written, based on this overall system performance. And so rather than just immediately write things, sometimes the operating system saying, gosh, I'd have better performance if I read these first two as the disk head is moving across the disk. And we'll take a look at how that impacts performance. So traditionally, we thought of mass storage just purely as a magnetic disk. We've pretty much gotten past the fact that sequential tape is a player anymore. We used to use a lot of tape for backup, but today it just makes probably much more sense for everybody to be backing up to a storage area network or even a cloud-based solution. And so we'll probably at some point soon see the last tape drive used. As we talked about, tape drives were sequential in nature. They had a lot of storage capacity. That was their big advantage. Their disadvantage was their sequential nature meant we had to read the start of the tape to get any content in the middle or at the end. And so that's why the cloud-based systems or storage area network-based systems are becoming better solutions for backup, so you can just get the data much faster. But when we talk about disk, we know that disk drive spins at a certain number of RPMs, and RPMs is just the number of rotations per minute. And so we can actually further, using math, knock that down to rotations per second. And typically we would see that disk drive is spinning at 60 to 250 times per second. So despite the fact they're mechanical, they're still moving really fast. And so one of the first things that we look at as we're shopping for disk is its RPM or its RPS, number of rotations per minute or second. So we can get a feel, because the faster the disk rotates, the faster the read-write head can get to information on the disk, and hence better overall system performance. And so a second indicator is the transfer rate, which is the speed at which the disk drive can transfer data to a memory buffer or a RAM location that the CPU can then access. And as part of that, we have the disk drive is moving back and forth as the disk drive is spinning, so we can get 2 sectors on the disk. And so that time for the head to move from one track to the next is basically called the positioning time or seek time. And so we need to know the 2 factors that come into actually impacting performance for a read-or-write operation is, first, we have to move the disk drive read-write head in or out to a specific location, track location, and then we have to wait for the corresponding disk sector to spin past. So we have 2 delays. We have the seek time, and then we have the rotational latency. And then finally, it doesn't happen as much anymore, but it used to happen a lot. The disk drive head would come in contact with the disk surface, and we'd have a head crash or a disk crash. And, oh gosh, it was probably most common in the past by just jostling a computer. But today, or in the past, even smoke could get into the disk drive, and so the space between the disk drive read-write head and the surface was so small that a hair, a piece of dust, a piece particle of smoke could cause a crash, and basically we would scrape all the storage medium off the surface of the disk, and thus everything that was stored in the disk was bad. And ideally, when you had a disk drive crash, and they happen, you hope that didn't happen in a critical file or in an area that was being used, because sometimes you could still salvage the disk despite the fact that the surface area had been damaged. If it happened in an area that contained overall directory information or partition table information, then you're pretty much out of luck. And today you can send the disk to a third-party vendor who can then still read the magnetized ones and zeros off of the rest of the disk. So you can probably still recover information. And so despite our best efforts to trash the disk, a lot of the information still becomes readable. So we've talked about the fact that a disk drive is spinning. Typically, most disk drives consist of multiple platters. And a platter is just kind of a photo album kind of storage surface area. And so we have multiple platters, and we have a read-write head that moves in and out across that platter to get to specific tracks on the platter. And when we're talking about a single disk drive, we'll talk about a track. If we're talking about multiple disk drives or multiple disk surfaces, we'll talk about cylinders. And so a cylinder and a track is kind of synonymous, but in this case we've got 3 tracks in our cylinder. And so to improve performance, because the disk drive head's movement is the slow process of all this, we might store information leaving the operating system in cylinders so we can access those things simultaneously. And so that's why the concept of cylinder is important, because we're moving the read-write head in and out, then we're waiting for a sector to spin by. And so we've got that movement and that rotational latency delay. So if we can put things in common cylinders, then we can improve performance. So how big are these platters? In general today, they're pretty small. You guys have probably installed a hard drive on a system, and so they're 3.5 inches, maybe even smaller. And we've talked about the fact that for phones and tablets and even new Mac computers, it no longer makes sense to have a disk drive, but instead we'll use some kind of flash memory instead. But logically, from the operating system perspective, we can just view it as a storage medium. But because the flash memory doesn't have movement and things, it's going to perform better because we don't have rotational delays, we don't have seek delays, than our hard drives will. And so as technology evolves, so will too our storage capacity within flash drive-based systems. And gosh, you can still get one today that's got terabyte storage capabilities, so huge storage capabilities. And so we will probably see soon, 5 years, the end of a lot of disk drives and within systems, and we'll find them more in storage area networks where they're providing backup capabilities to systems, because they always will have large storage capacity. And so when we talk about disk drive performance, we have to take those two considerations into account. How long it takes to move the read-write head to the proper track, and then that rotational delay. And so we refer to those delays collectively as our access latency. So it's our seek time plus our rotational delay. And so we can see some times here. And so in most operations, the slowest thing that's going to happen is going to be our disk access. Because let's think about a database system, for example. To perform a large query, we have to read a lot of records which are on disk. And so we're now starting to hear the terms memory-based SQL, no-disk SQL, where we're trying to keep our entire databases in memory because memory has become so expensive, such large capacity, that if we can get this mechanical process out of the loop, our systems are just going to perform faster. And even here, and this is something that you should be able to do the math on for exams and things. We want to be able to figure out what's going to be our average input-output time, because that's going to give us an indication of what's our overall system performance if we're disk laden. And so as we start to think about these things, our access time for local disk access, the hard drives part of our computer, is going to be faster than a storage area network-based system that resides on our current network, which is going to be faster than a cloud-based disk access. But our file system and our operating system should make all of those types of disk access appear similar to our programs or users who are clicking on file folders. They should not care whether the storage medium is or what the storage medium is. But we know that we're going to, based on the type of storage, have a different performance. And so here's a 1956 picture of a computer, one of the first commercial disk drives. And these things were huge. And oh gosh, we used to have 500 megabyte disks that were heavy enough that you knew it when you picked them up. And this was not that long ago, so Moore's laws continue to be true. And if you haven't seen Moore's law, it's worth a Wikipedia search. But it basically says the speed of a processor and the storage capacity of a disk drive is going to double every 18 months. And so processors just get faster and disk drives just have greater storage capacity. And so it's because our technology gets finer, we can represent a 1 or a 0 with just a smaller space on disk. And so hence our disk drive storage capacity starts to increase. So this was one of the early models, and today you have probably, oh gosh, maybe 1 million times the storage capacity of this system in the hard drive on your system, on your computer, and probably in flash memory in your phone. And so we've talked about the fact that there are solid-state devices and disks, and so they're going to be slightly more expensive. They're not going to have the same storage capacity, but they will be faster. And so you go shop for a Mac today, and you're no longer talking about a hard drive. You're talking about flash-based memory. We made reference to the fact that magnetic tape is probably going to disappear because, one, it's sequential in nature. It does provide a lot of storage capacity, but so too does cloud-based systems. And so it served its purpose well. It was a backup medium for a lot of years, and even before that, I've actually written programs that access data directly from tape. And that wasn't that long ago. So we're seeing the evolution of storage medium evolve really quickly. But mag tape doesn't work, and disk drives don't work, and devices like a Google Glass or a wristwatch or a mobile phone. So we're going to see more and more solid-state disk drives come around. And the nice thing about that is our applications will need to change because the operating system will shield us from the change in technology. Well, let's take a look at some of the underlying storage things that happen within a disk. And so a disk has areas that it can store information. And we'll typically refer to those as a block. And the block, depending on the system, might be 512 bytes, it might be 2K, it might be 64K. The larger the block size, the more information of a file we can store in the same block. But the larger the block size, if we have a file that's only 3 bytes long, and our block size is 64K, then we've wasted most of the 64K. Now, if we ever grow the file, it's going to be faster. If we read the file, it's going to be faster. But the larger the block size, the more opportunity for wasted space we have. So we could end up having a very large disk, which had a very large block size, but a lot of that block size was wasted because our file system aren't as large. Or if we had a file that required just over 1 block, then a lot of the second block is wasted space as well. So as you start to think about block sizes, if you just had large files, then the larger your block size, the faster your performance. You can grab more of a file in one read operation or more one write operation. But if you have a lot of small files, the larger your block size, the more wasted space you have on your system. So how do we connect disk drives to our systems? Most of them are connected right now to the primary bus within our computer, and that's for speed purposes. But if we have external drives, for years we used a SCSI connection, and I think it stood for Small Computer System Interface or something. But it was just a collection of wires that allowed us to have a bus to which we could plug in a disk drive externally to our system. And we could kind of daisy chain them, or we could plug multiple drives in, and so we would end up with multiple devices. Today, most disk drives external to our system connect via Ethernet or via our network, and so they're called storage area networks. So they're using our network communication capabilities to just directly connect to our system. So when you hear the acronym SAN, that's Storage Area Network, it's just a way to externally connect disk to our system. Well, when I had a SCSI connection, I was directly connecting 1 disk drive or 2 disk drives to a PC. And so those disk drives are available to those PCs, not all the PCs in the network. When I connect a disk drive to the SAN, then they're available to any system in the network. And so even in my home system today, I have SAN-based disks that are accessible to other computers, even in a Wi-Fi network. And so we've talked about the fact that most disk drives have multiple platters. Well, today we kind of work in terms of storage arrays. We have so much capacity demand that we combine storage capabilities, and so we'll use the terminology RAID, and it's a redundant array of independent disk drives that allow us to do several things. One, store information across multiple disks. And so when we retrieve the information, one disk can be busy, the second disk can be gaining additional information, a third disk can be gaining additional information. So we may have some performance gains. One can be reading a part of a file, one can be writing part of a file. So by spreading it out, we improve performance. But then you also say, well, you've got multiple points of failure. But the way that most RAID systems work is that we'll store redundant information, and we're going to talk about RAID systems in specifics, across each one of the disk drives. So if one of the disk drives go bad, we can almost rebuild on the fly the information that was on the disk that went bad, because we're storing redundant information, hence the R in RAID, across the other disk drives that allow us to perform these operations. So it would take multiple disk drives to go bad before we'd actually lose data. And so we'll talk about some of the RAID formats here. But so we have our storage array, and it's just kind of think of it as multiple disks that may appear as one. They're connected to a SAN, which is just our network. From the SAN, servers can get to them. We could replicate them. We could have them being copied in real time to a co-location facility, and users can get to them from the local or wide area network, either via servers or even just direct access. And so The storage area network is nothing more than disk drives connected to our network, and when we access a disk, behind the scenes, the operating system's performing the operations that are needed so that we can get to the content, despite the fact that we're doing it over a network as opposed to some other type of bus. And so we'll see the term loon, and it's a logical unit number. So we have all these disk drives out on the network. We need a way to access each one and identify each one, and typically that's done through a logical unit number. And so the operating system is hiding a lot of this detail from us, and so disk drives just appear, and they appear to have a drive letter. Behind the scenes is where logical unit numbers and things start to come into play. And so a SAN is our storage area network. A NAS is a device that's connected to such a network. And so typically we'll have, here you can see clients directly accessing our network attached or our network accessible storage, our NAS, just over the network. And so they don't know they're performing network operations, they just know they're performing disk drive operations. The operating system is doing the interface for us that allows for the process to appear pretty transparent. And networks, years ago, weren't fast enough to do disk drive operations, but with gigabit networks, it just becomes part of the network traffic that's flowing. And so we know that if we're using a disk drive, it's a mechanical device and means it has movement. The disk arm moves, the disk platter spins, so those are slow but in comparison to our random access memory, which is purely electronic. And so the operating system knows that it needs to write data to specific blocks. It knows which blocks because the file system is telling it that the second part of this file resides in block 4096. And so as the disk drive is spinning, the operating system can say, what order does it make sense for me to read or write sectors from? I've got all these programs that are running, I've got all these users that are running multiple programs, they're all doing disk drive operations. So I've got a request queue of a bunch of sectors that I need to read. And based on how the disk is spinning right now, what order would it make the most sense from a performance perspective to do that? And we can perform these calculations fast because the CPU is doing them, they're in memory, and so it's not relying on the mechanical slow disk drive. So based on how long it's going to take to seek to a sector, the operating system can make a determination. I should read sector 1, I should write sector 4, I should read sector 7, I should read sector 9, and kind of get an order that it's going to perform its operations in. And we refer to this process as disk scheduling. And so it's done by the operating system. And so if we look at the bottom of the slide, you can see that it's got a bunch of sectors it needs to read. And that this read-write head is currently pointing at sector 53. And so if it's pointing at sector 53 and it's spinning, it might make sense to read sector 65 and 67 next, as opposed to moving in or out or waiting for the rotational delay to get to other sectors. And so this is where we're trying to take a slow device, a slow mechanical device, and improve performance. And so if we just did it in order, you can see the number of movements that this read-write head has to make. And we can kind of say, okay, how long would that take based on the speed at which the disk platter is spinning? Not to mention whether or not we have to move the read-write head in or out, but let's assume that all these sectors are on the same track. Then we have to wait for the rotational delay for each one to ride by. So we'll end up with some performance numbers. And so the algorithm I used was the shortest seek time first, SSTF, that says the next sector you should read should be the one that's going to spin by next. And so this shows that we've removed, by doing SSTF, shortest seek time first, operations, we've reduced a number. But shortest seek time first still may not be the ideal algorithm because depending on spin rates, seek times, and so on. So there's different algorithms. And the scan algorithm, sometimes called the elevator algorithm, says, okay, if I get on an elevator and everybody pushes a button, it probably makes sense to be a little sequential in nature. And as opposed to going to the top and opening the door, and then going back to the bottom and opening the door, and then moving to the middle and opening the door. So an elevator algorithm is going to be kind of sequential with the shortest seek time first, ideally going in this direction that this read-write head is moving. And so again, we can take a look at and actually analyze how does this impact us performance-wise by using this algorithm. And again, our goal is just to say, okay, we want to reduce the fact that disk drives are inherently slow because they're mechanical. So C-scan is a similar algorithm, but it takes into account that a disk may have multiple cylinders. And so scan you can think of as a single platter algorithm. But now with C-scan, we want to take into account that we've got multiple cylinders, so maybe the next vector we read, based on where we're at with respect to our cylinders, changes. And so again, we've got some reporting and some analysis that we can do based on this. And so you should be able to, given a queue of disk drive requests, kind of state the order that these different algorithms would retrieve data for optimal performance. And so look is a version of C-scan, C-look, and so again, we're trying to reduce, we've got the rotational delay, but one of our longest delays is that moving the disk read-write head in and out because it's more of a movement. We know that our disk is spinning at 60 to 250 times per second. So it's spinning fast. And so our biggest delay that we want to get rid of is moving that read-write head. So C-look is another algorithm. And you should have a basic understanding of just how these algorithms differ. So how do we know which one to use? And so the operating system's got to decide. And so can it decide based on the speed that the disk drive's rotating, the speed of the access time, the speed of the disk arm? So all those things come into impact. And then in an ideal world, we run some analysis on it, and this isn't really something that we can easily change despite that. So that's disk scheduling. Now let's talk about disk formatting. We've talked about the fact that a disk has blocks of data that it reads, blocks of data that it writes. And depending on the system, a block might be 512 bytes, it might be 64K bytes. And so how do we know? Well, all this occurs when we low-level format our disk drive, where we specify the attributes of our drive. And so to begin, we've got one disk drive often. And so one of the first things we can do is partition that disk drive into logical drives. Now, they're logical drives because we only have one physical drive. But to the user, it may look like we have a drive C, a drive B, a drive E, because we've broken them into partitions and we made each partition a logical drive. And so all this information has to be stored somewhere. And typically the disk will have a master boot record within which it says, these are the partitions I know about. And the number of partitions we can use is not unlimited. Most will restrict it to 26, so we can have letters of the alphabet assigned to each disk drive. And so in the master boot record, it will say partition, my first partition, which corresponds to drive C, is this big, this many tracks, this many sectors. And the second partition, which would be drive B, is this big. So all that's stored out on the disk. So when your computer boots, the operating system goes out, reads that master boot record, and says, okay, I know where my partitions are, I know how big they are, I know how many I have. And so that's just part of our startup process. Once we've partitioned our disk, we have to format the disk for use. So we could format drive C for use by Windows, we could format drive D for use by Linux, and in that format process, we're basically going to create the file system on that disk. So we're going to define the block size, so we know how big or how much information the drive's reading and writing at any given time. And we're also going to create an initial directory structure out there. And we're going to create a file allocation table or inode table, fitting our operating system, which is going to track the actual locations of each file on disk. So here's kind of what we have. In Windows, for example, we said that when we boot, we read something called the MBR, the Master Boot Record. The Master Boot Record tells us how many partitions do we have, where does each one start. And so if you've got multiple operating systems installed on your computer, and when you turn on your computer, it says, which operating system do you want to start? The boot process has already gone out and looked at the Master Boot Record, said there's multiple partitions out there. It's kind of looked at each partition and said, wow, there's multiple operating systems out there. And so each one of these partitions is bootable. Which one do you want to boot from? And so even when we're doing just simple virtualization of our own system, by meaning we're going to put Linux out there, we're going to put Ubuntu Linux out there, we're going to put Windows out there, a different version of Windows out there. That's how this is happening. We're creating different partitions for each one of those systems. The Master Boot Record is keeping track of those. And so we've talked about the fact that when we run multiple programs at the same time, they don't always all fit in RAM. And so we'll swap one program out so we can swap another program in so it can run. And so to do that quickly, normally the file system will allocate some space out on disk in a contiguous. So you can think of the words consecutive, you can think of the words contiguous. Contiguous is kind of a block of closely grouped blocks. Space, so it can quickly access all the swap space in a hurry and then manage that swap space. And so part of the file system will say, okay, I'm going to create my directory structure, but I'm also going to allocate additional space so I can swap programs in and out, manage that quickly, to improve overall system performance. And so part of the file system's responsibility is this thing called our swap space. And so if we just have a big block of disk storage, the operating system is then free to assign a context, a structure to that storage. And so in this case, it's just going to swap processes in and out to that storage quickly and manage that area itself how it wants. So you can think of the swap space as just kind of a sequence of bytes. The operating system is going to put meaning to those bytes. So bytes 0 through 2K is the first process we've swapped out. Second process is a lot bigger, so it goes 2K to 64K. The operating system can manage the swap space. Now, we've talked about RAID in this conversation, said that RAID stands for Redundant Array of Inexpensive Disk. You'll sometimes also see the term RAID as a redundant array of independent disks. So the concept is we've got a bunch of disk drives out there where we're going to collectively use them to store our file system. And so by spreading data across multiple disks, one disk can be being read while another one's being written, while another one's being seeked. So we should have better performance. But again, when we have a RAID system with multiple disks, we now have multiple points of failure. And so we try to keep track of how frequently should I expect a disk drive to fail. And so we'll call that the mean time between failure, the average time to failure. And so how do they calculate that? Well, in general, they'll take, well, let's call it 1,000 disk drives, and spin them all up and let them be used. And so we've got 1,000 disk drives running. And the first one fails after 500 hours. It just breaks. 500 hours isn't that long. What is that? It's just surely over 3 weeks. But because we had 1,000 disks running, they'll say the average time to failure is 500,000. 500 hours times 1,000 disk drives gives us 500,000. So we should expect that our disk drive should run 500,000 hours before it fails. That gives us some indication, but that's really not fair because no disk drive in the survey or in the study ever ran 500,000 hours. So you need to understand how mean time between failure is calculated, and just kind of have that in the back of your mind. But because we have multiple drives, we have multiple points of failure, so one's going to fail. So how RAID works is that it's going to store data across the multiple disk drives, so that if one disk drive should fail, we've got redundant data that we can almost rebuild on the fly the content of that last disk drive. If two drives fail, we can restore on the fly that content. And so it's because of this redundant data that's out on those disk drives. And why can we get away with that? Because Moore's law tells us that the storage capacity of a disk is going to double every 18 months. So we will eventually get to a point where we can just have lots and lots of disk space. So let's use it. Let's put some redundant data out there. And we'll, as long as the disk drives are working, we'll have better performance. And should one fail, we'll just rebuild its contents. And so with RAID, we refer no longer to blocks, but to stripes of data. And so you don't really need to have an understanding of how RAID version 4 differs from RAID version 5, or this differs from RAID version 6. You should have an understanding of RAID 1 is the most basic, and then current versions of RAID, where they're kind of at, and know that the higher the version number, the more complex the redundancy built into it. But understand the downside to RAID is we're going to use multiple disk drives. That means multiple points of failure. But we're going to put redundant data out there, so that means we're not making the very, very most optimal use of our disk space because we've got redundant data out there. The disk space is inexpensive, disk space is growing every 18 months, and so that's what makes RAID work. So here's some of the different levels of RAID redundancy. You should understand that if we've got multiple RAIDs out there. Now let's take a look at RAID 0. We have no redundancy. RAID 1, we're basically saying, I've got 4 disk drives, I'm going to use 4 more to mirror their content, make an exact copy of it. And then RAID 2 is going to use error correcting code, so should one of the disk drives go down, that redundant error correcting code is going to allow me to rebuild it. RAID 3 is going to use even a more sophisticated technique until we finally get down to RAID 6, and it's using parity, it's using distributed parity, it's using blocking or leaving, it's using error correcting code, so it's going to give us the greatest amount of redundancy, so should multiple disks fail, we can rebuild them on the fly. So pretty cool. And the neat thing about this is it's implemented at the hardware level, and so our operating system doesn't really care that we've got a RAID disk out there. It doesn't care how many platters it has. It just knows that it's got a logical storage capability out there. And so we're going to talk about in future chapters how RAID plays into our redundancy and disaster recovery process, and it does and it should. The neat thing about it, though, is, again, from the operating system perspective, we don't care that it's a RAID disk out there. And again, you don't necessarily need to know all the technology behind RAID, but you should do a little drill down today to say, okay, I want to buy disk array. What level of RAID is it? And does the level of RAID change the cost, for example? And we're not going to get into checksums. We'll see checksums in disk operations. We'll see checksums in network operations. And so, from your perspective, checksums allow us to detect whether or not we have an error, as does parity. And so a lot of the issues that will come up in network communications also comes up in disk operations, whereas we can read a disk and get an error. And if we had a parity error, then one bit could cause the entire block to be bad. Error checking codes allow us to have better understanding of which specific bit was bad. Error correcting codes allow us to make a correction to that bad bit. And so you just need to have kind of an understanding of what's the difference between an error checking code, a parity code, and an error correcting code. Not going to drill down into pooled storage systems or stable storage systems. But you guys should go out and take a look at what's the current storage capacity that's available on Mac through flash-based memory versus what's available on a Dell system through different storage technologies, different storage medium. And so I've already captured who is here. I appreciate you guys all being here. I should have more specifics on grades later this week, and so I'll get those posted. And watch for me to post one more chat on file systems, because I want to kind of go over the implementation of file systems. It's worthwhile for you to listen to. You don't need to get into a lot of the nuts and bolts of how the file systems work behind the scenes, but you need to have a conversational ability to say, okay, this is how I would track how a file is stored in Windows, this is how I would track how a file is stored with Windows and Unix. But beyond that, probably not so much. So have a great week. I will see you. I posted a couple file system discussion threads, so jump out in those, and again, I'll use those as kind of extra credit. And I'm going to turn off the recording on this so we have it. And if you have any questions, other than questions on grades, because I'm still working on grades and things this week, post them in the threads. Otherwise, have a great week.